Okay, let's dive into something pretty amazing. We're going to talk about the strange, mind-bending math that is secretly running the GPS in your phone right now. It turns out, every time you look up directions, you're helping to solve a puzzle that's over 2,000 years old. I mean, have you ever really stopped to think about it? How does your phone know, down to just a few feet, exactly where you're standing? It feels like magic, right? But it's not. It's actually a story about an ancient mathematical problem that found its solution in the very fabric of the universe itself. Because here's the crazy part. If your GPS used the normal geometry we all learned in high school, Euclidean geometry, it would be completely, totally useless. We're not talking a little bit off, we're talking catastrophically wrong. Every single day, your location would drift by almost 12 kilometers. In less than a week, it would think your house is in the next town over. So what saves the day? What keeps us on the right track? This. A tiny correction of just 38.7 microseconds that gets applied to the clocks on the satellites every single day. This minuscule number, well, it's the hero of our story. And to understand where it comes from, we have to go way, way back to ancient Greece. And that takes us to the man himself, Euclid, the father of geometry. Around 300 BC, he basically wrote the book on how space works. He built this incredible system on just 5 simple rules, or postulates. But one of them was a little bit sketchy.
The first 4 rules are things that just make sense. You can draw a straight line between any 2 points. You can extend that line forever. You can draw a circle, all right angles are equal. No surprises here, right? In fact, these 4 rules are so solid, they form what's called absolute geometry. They work perfectly for just about anything you'd ever want to measure in your day-to-day life. But then there is the 5th rule. The famous parallel postulate. The original wording was a bit of a mouthful, but it boils down to something like this. If you have a line and a single point not on that line, there is exactly one other line you can draw through that point that will never, ever cross the first one. Now, it feels true, but it wasn't as obviously, self-evidently true as the others. And it seems even Euclid knew it was weird. He avoided using it in his proofs for as long as he possibly could. And this just shows you how long that doubt lasted. For 2,000 years, the smartest mathematicians on the planet tried to prove this 5th rule using only the other 4, and every single one of them failed. It was the longest-running mystery in mathematics, until a few brave thinkers in the 1800s started asking a totally radical question.
What if the parallel postulate wasn't a law of the universe you had to prove? What if it was a choice? What if you could just change it? Guys like Bolyai, Lobachevsky, and Gauss had this wild idea that you could deny that 5th rule and still build entirely new, perfectly logical geometries. You could create whole new mathematical universes that work just fine but followed different rules. And this, right here, is the game changer. Euclidean geometry says there's exactly one parallel line. But these revolutionaries asked, what if there were none? Or what if there were infinitely many? Just by changing that one single assumption, you create entirely different ways for space to behave. So let's break down these 3 universes. You've got your flat, Euclidean space. That's the one we know. One parallel line, and the angles in a triangle add up to exactly 180 degrees. Simple. But then you have hyperbolic space, which is kind of saddle-shaped. There, you can draw infinite parallel lines. And in spherical space, like the surface of the Earth, parallel lines don't exist at all. Eventually, they all cross. And this has some really weird effects on something as simple as a triangle. Okay, so this is the one we all learned in school, right? You draw any triangle on a flat piece of paper, add up the angles, and you always get 180 degrees. It's clean, it's predictable. But on a curved surface, like a sphere, things get weird. Imagine drawing a triangle on a globe. Okay? Start at the North Pole, go straight down to the equator. Now take a hard 90-degree right turn and walk a quarter of the way around the planet. Then take another 90-degree right turn and go straight back up to the North Pole. You just drew a triangle that has 3 right angles. That's 270 degrees. On a sphere, triangles are fatter, and their angles always add up to more than 180. And in that negatively curved hyperbolic space, the one that looks like a Pringle or a saddle, the exact opposite happens. The triangles are kind of skinny, and their angles always add up to less than 180 degrees. Now, for centuries, this was all just a cool game for mathematicians, a fascinating what-if. And then, a guy named Einstein came along.
Einstein's genius was realizing that these weird geometries weren't just abstract thought experiments. He proposed that they were a real, physical description of our actual universe. He took them out of the textbook and gave them a job.
This is the absolute heart
of his theory of general relativity. Gravity isn't some invisible force pulling you down. Instead, massive things like planets and stars literally bend and warp the four-dimensional fabric of space-time around them. So the Earth isn't being pulled by the sun, it's just following the straightest possible path through the curved space that the sun creates.
And that straightest possible path has a special name. It's called a geodesic. It's the universe's definition of a straight line, whether space is flat or curved. You see it all the time. On a globe, the shortest flight from New York to Tokyo is a great circle route, which looks like a big curve on a flat map. That's a geodesic. In the cosmos, everything from a baseball to a beam of light is just following its geodesic through space-time.
Okay, so here's where we bring it all home. Let's connect this cosmic idea back to your phone. We can finally solve that 12-kilometer error because those GPS satellites are living in a slightly different reality than we are. They're moving super fast, and they're in a place where space-time is curved differently.
First, you have to appreciate the insane precision required here. For GPS to work, the timing has to be perfect. An error of just 1/1000th of a second, a nanosecond, throws your location off by about a foot. So any tiny effect on the passage of time is a huge deal. And as we've seen in non-Euclidean spacetime, time isn't the same for everyone.
And what's happening is that there are two relativistic effects messing with the satellite clocks, and they're fighting against each other. First, because the satellites are moving so incredibly fast, Einstein's special relativity says their clock should actually tick slower than ours by about 7 microseconds a day. But, and this is the big one, because they're farther away from Earth's gravity, they're in a flatter part of space-time, so general relativity says their clocks should tick faster than ours, by a whopping 45 microseconds a day. So you just do the math. They speed up by 45, but they slow down by 7. That leaves you with a net gain of about 38 microseconds every single day. There it is, our hero number. Without correcting for this relativistic time shift, the entire GPS network would fail within minutes. In fact, engineers actually build the satellite clocks to run a little bit slow here on Earth, so that once they get into orbit, they speed up to the perfect rate.
So here's the really cool takeaway. Every single time you use Google Maps or Waze, you are personally running a real-world experiment that proves Einstein was right. You are proving that the geometry of our universe is non-Euclidean. Your phone is literally a pocket-sized testament to one of the greatest scientific discoveries of all time.
This journey, from a 2,000-year-old mathematical question to the technology sitting in your hand, is just one of the greatest stories in science. What started out as a purely abstract game, just playing with rules, it turned out to be the literal blueprint for space-time itself.
And that leaves us with one last fascinating thought. What other seemingly useless or weird mathematical ideas are being cooked up in university classrooms today? What future technology that we can't even begin to imagine is just out there, waiting for its strange new math to be born?